Chapter 7 has to do with quantities and chemical reactions, and the first chapter, or first part of the chapter that we're looking at, is stoichiometry. Stoichiometry is often compared to cooking, and because cooking is basically like applied chemistry. If you look at a basic recipe for pancakes, if you have each of these ingredients in the perfect amounts, you can make 12 pancakes. So therefore, you need each of these ingredients with the exact amount in order to make exactly 12 pancakes. Of course, if you wanted to make 24, if you want to double the number of pancakes, you'd have to obviously double the amount of each ingredient. If you wanted to just make 6, then you'd have to take each ingredient and divide it by 2. So how cooking is like chemistry is because each of these things together react and make 12 pancakes. We can also look at a recipe, for example, for ammonia, right? So 1 molecule of nitrogen will react with 3 molecules of hydrogen to make exactly 2 molecules of ammonia. So 1 of these, 3 of these hydrogens will make 2 molecules of ammonia. And we know this is correct because if you look at the number of atoms present, we have 2 nitrogens reacting together. And there's 2 nitrogens in the product. We have 6 hydrogen atoms in total and 6 hydrogen atoms in the products, right? So conservation of mass through our chemical reaction. So we can write this recipe for ammonia as a chemical equation. We can say that nitrogen plus 3 hydrogens will form 2 ammonias. And as you can see, that's just a balanced chemical reaction. Just like the recipe for pancakes, you need exactly 1 molecule and exactly 3 molecules to make 2 molecules. But as we've spoken about before, molecules are too small to work with, right? We don't work with individual molecules because that's just too small in chemistry. We work with larger quantities. So a larger quantity that we can work with is 1 mole, because 1 mole of something is 6.022 times 10 to the power of 23 molecules, right? So that's, quite a lot of molecules of nitrogen, and that's a measurable quantity, right? These are much more manageable, measurable quantities. So we can just use ratios for this reaction, much in the same way 2 cups of flour with enough of the rest ingredients will make exactly 12 pancakes, so 2 cups of flour for every 12 pancakes. We can create mole ratios for chemical reactions. So we could say 1 mole of nitrogen for every 2 moles of ammonia. So this is a ratio, 1 mole of nitrogen for every 2 moles of ammonia. So 1 mole of nitrogen required to make 2 moles of ammonia. You can also flip it and say 2 moles of ammonia will form if you have 1 mole of nitrogen present. And then we could also look at the quote-unquote ingredients or reactants of this reaction. So for example, if I have 1 mole of nitrogen, I need 3 moles of hydrogen, right? Alternatively, 3 moles of hydrogen for every 1 mole of nitrogen. And finally, the last permutation that we need to look at is between hydrogen and ammonia, and we could say 3 moles of hydrogen given enough nitrogen will form 2 moles of ammonia, and vice versa, right? Of course, these are just the reciprocals of each other, right? The ratio is still preserved. So this chapter is all about the relationships between the number of moles of products and reactants in a chemical reaction, and this word is called, this study is called stoichiometry, and these ratios are called stoichiometric ratios. Okay? I know it's a mouthful, but you'll get used to pronouncing it. So mole-to-mole stoichiometric calculations. So if 2.37 moles of nitrogen gas was present, calculate the maximum amount of ammonia that can be formed. Well, you might think to yourself, but I only have the ratio for nitrogen here in a 1:2 ratio. I don't have 2.37. Well, we can use ratios to find out how much ammonia will form given this amount, right? So we can just say if you have 2.37 moles of nitrogen, and I know that for every 1 mole of nitrogen, I can form 2 moles of ammonia, then I just input this into my calculator and I can calculate how much, what amount of ammonia can form. And so that would be 4.74 moles of ammonia. And conversion factors are kind of helpful to use here because, as you can see, the unit you have goes in the bottom, so it cancels out, and then the unit you want, which is moles of ammonia, goes in the top, and the relationship is that stoichiometric ratio. Take a look here. It says the minimum amount of hydrogen required to completely react this nitrogen gas. Well, if I had 2.37 moles of nitrogen, how much hydrogen would I need? So I need to pick the right ratio. Well, for every 1 mole of nitrogen, so for every 1 mole of nitrogen, I have, as you can see here in the chemical reaction, 3 moles of hydrogen required, right? So as you can see, these mole ratios right here are all constructed using the coefficients in the balanced chemical reaction. Okay, so I'm going to go ahead and calculate that now. And the answer there is 7.11 moles of hydrogen is required to completely react this 2.37. Okay, so I need to have 7.11 moles of hydrogen. If 5.98 moles of ammonia gas formed, calculate the moles of nitrogen gas that reacted. Okay, so we can go backwards. So say I started, or say I know that this is how much ammonia gas I formed. What's the relationship with nitrogen gas? Well, I know that for every, and I go back to my balanced chemical reaction, for every 2 moles of ammonia, I have 1 mole of nitrogen. That's my ratio. So I'm going to put that in here, 2 moles of ammonia, putting it in the bottom so that it will cancel right here. And the relationship with nitrogen is 1 mole of nitrogen. So my stoichiometric coefficient is 1 to 2. It cancels. And my final answer is 2.99 moles of nitrogen reacted. And we can do the same thing with the moles of hydrogen as well. But be very careful here because this one says molecules. So what I'm going to do is I'm going to first, I have moles of ammonia. I'm going to use my stoichiometric ratio to go to moles of hydrogen. And then from the moles of hydrogen, I want molecules of hydrogen. So I'm going to have to use Avogadro's number to get molecules of hydrogen. So I'm going to start off with 5.98 moles of ammonia, and I go back to my chemical reaction to look at the stoichiometric ratio. So 2 moles of ammonia for every 3 moles of hydrogen. So 2 moles of ammonia for every 3 moles of hydrogen. And again, the question didn't ask me for moles of hydrogen, it asked me for molecules of hydrogen. So for every 1 mole of hydrogen, I have 6.022 times 10 to the power of 23 molecules. And let's just verify that my units work out here. Moles of ammonia, well, those will cancel. Moles of hydrogen will also cancel. And so my final answer is 5.40 times 10 to the power of 24. So that's how many molecules of hydrogen there are, right? And as you can see, we tend not to work in these large numbers, so we generally just work with moles, and then from there we can go to a more measurable quantity. Looking on the back side here, we see we have some homework questions right here. numbers 4, 5, and 7. But we don't have a scale for moles, right? So we can find out how many moles are required using my stoichiometric ratios, but we have no scale that measures moles. What we do is we have a scale that measures mass, so grams. So we have to take this to the next step, which is actually going from moles then to grams, because that's something that chemists can measure out in the lab. So here we are, mass to mole stoichiometric calculations. These are essentially the same calculations as mole to mole calculations. However, there's an extra step in calculating mass. This is useful because moles cannot be measured directly, but mass can be measured using a scale. So let's take a look at this chemical reaction. This is just a double displacement. Aqueous iron 3 chloride plus aqueous sodium hydroxide reacts to form a precipitate of iron 3 hydroxide and aqueous sodium chloride. So if 2.50 grams of the sodium hydroxide were reacted, determine the maximum possible moles of iron 3 hydroxide that you can produce. So I'm taking 2.5 grams of this, and the question's asking, if I have 2.5 grams of this, how much of this can I make? Again, no different than the recipe for pancakes, right? If you have 2 cups of flour, you can make 12 pancakes. So the question is, if I have 2.50 grams of sodium hydroxide, how much of the iron 3 hydroxide can I make? So let's make a plan. I have grams of sodium hydroxide, and remember, to be able to use the stoichiometric ratios, I have to be in moles. So I go from grams to moles of sodium hydroxide. And then once I have sodium hydroxide, I can use the stoichiometric ratio to find the moles of iron 3 hydroxide. Okay, so that's my plan. 2.50 grams of sodium hydroxide. I'm going to convert that into moles using molar mass. Right? And so I need to calculate in 1 mole of sodium hydroxide, what's the mass of sodium hydroxide? Okay, so using my periodic table, I look up the masses of the different elements, add them up together, and I get 40.00 grams of sodium hydroxide for every 1 mole of sodium hydroxide. Okay. And this is going to be helpful, right? Because my grams and my grams will cancel, and then I'll be left with sodium hydroxide, moles of sodium hydroxide. But the question didn't ask me for the moles of sodium hydroxide. It says the maximum possible moles of iron 3 hydroxide. So then I have to go up to my chemical equation. Well, 3 moles of sodium hydroxide are required to make 1 mole of iron 3 hydroxide. And you might ask, well, why is that the case? Well, take a look. This formula contains 3 hydroxides. So those 3 hydroxides have to come from the sodium hydroxide, so I'll need 3 sodium hydroxides. So 3 moles of sodium hydroxide for every 1 mole of iron 3 hydroxide. Let's double check. This unit on top, this unit on the bottom, cancel. This unit on top, same unit on the bottom, cancel. And yes, I'm left with the unit that I want. And then I can just go ahead and punch those numbers into my calculator. Okay, my final answer is 0.0208 moles of iron 3 hydroxide. And notice that I am preserving 3 significant digits because that's what I started with, right? You might think, well, this only has 1 significant digit, but I know these are exact numbers. There's exactly 1 mole of iron hydroxide that comes from exactly 3 moles of sodium hydroxide. So these numbers have infinite number of significant digits. So you're only constrained by the 3 significant digits in the sodium hydroxide. Using equations, you can just say that, well, I need to get moles, so that's going to be mass over molar mass. So therefore, moles is equal to 2.50 grams over 40.00 grams per mole for sodium hydroxide. And so my moles of sodium hydroxide is 0.0625 moles of sodium hydroxide. Then I take 0.0625 moles of sodium hydroxide, and I use my stoichiometric ratio, same thing, 3 moles of sodium hydroxide for every 1 mole of iron 3 hydroxide, and I'll end up with the same answer. Okay, so again, different method, but reaches the same conclusion. Okay, and as you can see here, grams and grams would cancel. Mole is in the denominator of a denominator, so it would come up to the top, and we'd end up with moles of sodium hydroxide. Okay, final example here. If 5 grams of sodium chloride was produced, determine the maximum mass of iron 3 chloride that reacted. Okay. So now I'm going backwards. I'm starting with grams, and they want me to go to grams of iron 3 chloride that reacted. So, as you know, we start with grams of sodium chloride, and to use stoichiometric ratios, I need to be in moles. So I'm going to go from grams of sodium chloride to moles of sodium chloride, and to be able to do that, I need to use molar mass. Okay, you can maybe, if you want, you can write the like what you need to do over the arrow. And then once I have the moles of this, I can use stoichiometry to go from moles of this to moles of this. So I can just use stoichiometry, the stoichiometric ratio, to moles of iron 3 chloride. And then moles of iron 3 chloride, it's not what it asked. It asked the mass of iron 3 chloride, so I need to go to grams of iron 3 chloride. And when you go to moles to grams, again, that's using the conversion factor of molar mass. Okay, so let's set this up. And this is kind of nice because using conversion factors, it'll all be in a row. So 5 grams of sodium chloride times 1 mole of sodium chloride, all over the molar mass of sodium chloride, so that's 22.99 plus 35.45, and that gives me 58.44 grams of sodium chloride. And I can see, yep, units are going to cancel. Stoichiometric ratio, well, what's that ratio between sodium chloride and iron 3 chloride? Well, I need 3 moles of sodium chloride to make 1 mole of iron 3 chloride, and that makes sense because iron 3 chloride has 3 chlorines and sodium chloride just has 1, so I need 3 of them. So I construct the ratio. Well, moles of sodium chloride, that's 3 moles of sodium chloride produces 1 mole of iron 3 chloride. Again, where am I getting these numbers? Right up here, 3, 2, 1, right? 3 moles of sodium chloride for every 1 mole. Again, no number there, but we know that it's assumed to be 1. And then mass of iron 3 chloride, well, we just have to calculate what the molar mass is. So every 1 mole of iron 3 chloride has what mass? And that's 162.20 grams of iron 3 chloride. And then this is just a matter of inputting it into our calculator. And my final answer would be 4.62 grams of iron 3 chloride. And let me just double check that the units are okay. Grams of sodium chloride, that works. Moles of sodium chloride, moles of sodium chloride. Okay, that cancels, and I'm left with the units that I want. Okay, so this all works out. And then you can do this with equations much in the same way we did it up here as well. Okay, but I'm not going to include that in this video. Thanks for watching.